Imagine standing on a vast, invisible stage where every object, from tiny pebbles to massive stars, plays a role in a cosmic dance. You, the Earth, never quite drift away into empty space because of a delicate balance, a tug-of-war between two simple ideas, a pull inward and a motion outward. This is why planets orbit. Long ago, people thought planets moved because of mysterious forces or perfect circles drawn in the heavens. Today we know the story is simpler and more elegant. Everything with mass pulls on everything else. This pull is gravity. The more massive an object, the stronger its pull. The Sun, enormous compared to Earth, exerts a significant gravitational tug. Left to itself, Earth would fall straight into the Sun. But Earth also carries motion, is traveling sideways through space. That sideways motion is inertia. Objects tend to keep moving in a straight line unless something changes that motion. Picture standing in a field and throwing a ball. If you throw it gently, it arcs and lands nearby. Throw it faster, it goes farther. Imagine throwing it so fast that as it falls, the surface beneath curves away at the same rate. In that thought experiment, the ball would never hit the ground. It would keep falling around the planet. That is essentially what an orbit is, falling forever but missing the ground. The balance between the Sun's pull and the planet's forward motion creates a stable path. Not a tug-of-war where one side wins, but a continual compromise that loops the planet around its star. To understand the tug-of-war language, think of it as a contest between two tendencies. Gravity tries to pull the planet inward, while inertia tries to carry it straight outward. Neither side wins completely. If gravity was stronger, or the planet moved slower, it would spiral inward and likely be consumed by the Sun. If the planet moved much faster, it could escape the Sun's pull and drift into deep space. Most planets settle into a middle ground where gravity curves their straight-line motion into an ellipse, a slightly squashed circle. That is why planets trace reliable paths year after year. You might ask why orbits are stable instead of chaotic. Part of the answer is conservation laws, particularly conservation of energy and conservation of angular momentum. These are like bookkeeping rules of motion. Energy decides how bound a planet is to its star, whether it remains trapped in orbit, crashes in, or escapes. Angular momentum, which depends on how fast and how far the planet moves, prevents sudden changes. Unless something large and external disrupts the system, a passing star, a giant asteroid impact, or a slow drag through a gas cloud, planets keep their orbits for billions of years. Not all orbits are perfect circles. Johannes Kepler discovered that planets move in ellipses, not exact circles, with the Sun at one focus. That means a planet spends some of its journey closer to the Sun and some of it farther away. When it swings nearer, gravity strengthens and the planet speeds up. Farther out, gravity weakens and the planet slows. This constant exchange between speed and distance keeps the orbit consistent, like a runner easing through turns to maintain pace around a track. The tug-of-war metaphor helps when we consider moons, rings, and spacecraft. Moons are planets in miniature, held by their planet's gravity while orbiting sideways because of their motion. Spacecraft use this same interplay when engineers perform gravity assists, stealing a tiny bit of a planet's momentum to slingshot a probe further into the solar system. Even tides are a manifestation of gravitational tugging. The moon's pull stretches Earth's oceans, creating a daily rhythm. In the end, the beauty of planetary orbits lies in their simplicity. No invisible strings, no guiding hands, just gravity and motion in a constant, measured contest. Planets orbit because they are continually falling toward their star, while simultaneously moving forward fast enough that they never quite reach it. That elegant compromise is the reason the skies look ordered and predictable, and why our world, suspended in space, remains exactly where it needs to be.